Questions 21 through 25 on the 2008 grade 12 AMC 12A. A permutation A1 through A5 of 1, 2, 3, 4, 5 is heavy-tailed if A1 plus A2 is less than A4 plus A5. What is the number of heavy-tailed permutations? What we need to do in this question is figure out a scenario in which this is true in a permutation of those 5 numbers. So for example, this would be valid. 1, 4, 2, 5, and then the 3 in the middle. This is one such permutation. Why? A1 is 1, A2 is 4. A1 plus A2 would therefore be 5. A4 and A5 are these two, and A4 plus A5 is 7. So since A1 plus A2 is indeed less than 7, this is a valid permutation. We have to find how many of those there are. So if you do it in a systematic way, it shouldn't be too bad. So here we go. So let's begin. 4, 5. I'm going to start with 4, 5 like that. If 4, 5 are my last two, A4 and A5, that is what I've set, then the first two can be any of the following. 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, or 3, 2. Any of those would be valid for A1 and A2. So how many do I have in total? 6 permutations. And then the exact same will hold true if I reverse the order for A4 and A5. It'll be the exact same 6 that I can create. All right, so that takes care of 4, 5, and 5, 4. Now I will make A4 and A5 3 and 5, like that. And now let's see what we have in terms of A1 and A2. A1 and A2 could be 1, 2. They could be 2, 1. They could be 4, 1. 1, 4, 2, 4, or 4, 2. So as before, we got 6 there. All right. And when you reverse the order from 3, 5 to 5, 3, it's exactly the same with regard to what you can put for A1 and A2. So that's another 6. All right, moving right along. The next one, I'm going to use 2 and 5 for my A4 and A5. And if I do, the possible choices for A1 and A2 are 1, 4, 4, 1, 1, 3, 3, 1, and that's it. So this is 4. And in a very similar way, if I were to reverse the order of A4 and A5, I would get another 4. It would be exactly the same as these guys. All right, moving along to the next one, there's 5 and 1. For A4 and A5, and if that is the case, the only possibilities for A1 and A2 are 3, 2, and 2, 3. So those give me 2 right here. And very similarly for 1, 5, it would be the same thing. We'd only have 2. Okay, so I think we've exhausted the 5s. Now we move on to the 4s. So 3, 4 is my first one. That gives me the possible choices as follows: 1, 2, 5, 1, 5, 2, 1, and 2, 5. And that's it. So this is 4. And in a very similar way, you'll get 4 if you reverse the order and write 4, 3 for A4 and A5. So I think we're almost done here. We got, what's next here? 2, 4. For my values of A4 and A5, this possibilities are 1, 3, and 3, 1. And that's it. So there's only 2 for that. And similarly, there'd only be 2 for 4, 2. And then we're down to 4, 1. If you have 4, 1, there's no way that you can make A1 and A2 less than A4, A5. If you try it, you'll see. So that means there's a 0 for that, and therefore 0 for 1, 4 as well. And then, let's see, if we keep going, how many do we get? For 3, 2, you get 0, 2, 3, 0, 3, 1, you get 0, 1, 3, you get 0, 2, 1, and 1, 2 also. None of these will be possible to create anything like that if these are chosen to be A4s and A5. So this is 0, 0, 0, 0, 0. So let's count them all up. We got 4 plus 8 is 12, 12 plus 4, 16, 16 plus 8, 24, and 24 plus 24 is a total of 48. And therefore, number 21, the answer is D. A round table has radius 4. 6 rectangular placemats are placed on the table. Each placemat has a width 1 and a length x as shown. They are positioned so that each mat has 2 corners on the edge of the table, these 2 corners being endpoints of the same side of length x. Further, the mats are positioned so that the inner corners each touch an inner corner of an adjacent mat. What is x? The trick in this question is to draw a triangle, and that will help us through Pythagoras figure out the value of x. And that triangle is as follows. It's from this point right here down to here, and then from that point to here, and then across like that. And that is, of course, a right triangle right here, since they have told you that those are rectangular mats. And let's start labeling this. This point right up here I will call A. This point down here will be B, and this point C. So those are the vertices of that triangle. A to C is just x, right? And let's see, A to B represents the diameter. And since the radius is 4, A to B is equal to 8. And then now I have to look at B to C. Well, this little distance right there, that is 1. That guy right there. Okay, so I'll put a 1 right there. And then similarly, this distance is also a 1. So I'll put 1 there. And then now I have to get this distance from here to here. So let's label that. We'll call this point E, and then I can call this point F, I guess. So if I can get EF in terms of x, then I'll be able to solve this in terms of Pythagoras. Well, the good news is that this is also x, and this distance is also x. So now we have to think about this triangle right here. Is there some way I can get EF in terms of x? And the answer is absolutely. What you have to do is first and foremost understand that this inner shape gives us a clue to the angles. Okay? The angles are going to be very important in this question. And this shape, it's 1, 2, 3, 4, 5, 6-sided shape. The sum of the angles of all the interior angles, all those guys, is equal to 720. So to get the angle in terms of each individual angle, you would just do 720 divided by 6. And that is, of course, equal to 120. So each of these guys is 120. So that is going to be 120 degrees. I'll just write it over here. And then the good news is now that we have the angle, we can figure out EF in terms of x. What I'm going to do is actually going to cut it in half. So cut it down the middle like that by dropping a perpendicular. If I do that, I think it makes it a little bit easier. Because since this was 120, when I cut it in half, this becomes 60. And this is, of course, a 90-degree angle, and this is 30. So there we go. Once again, we've got a 30, 60, 90 relationship. for probably the 100th time on a math contest. So I can figure out this side in terms of x. Okay? And that side, of course, from here to here is EF over 2. So EF over 2 over x is going to be the ratio of the sides. And the ratio of the sides are always 1, 2, and root 3, as always, in a 30, 60, 90 triangle. So looking at the ratio, EF over x is going to be root 3 over 2. Okay? So therefore, EF over 2 is root 3 over 2x, and therefore EF is equal to root 3x. All right, so now we have to basically do the Pythagorean relationship on this big triangle right here. Okay, so we've got AC squared plus BC squared is equal to AB squared. AC is just x. BC is this whole distance from there to there. And that's going to be 1 plus EF, which is root 3x, plus 1, right? This one plus EF plus this one. And that's all squared. And then AB squared is 8 squared. Right, so this is the equation we have to solve for x. So here we go, x squared plus root 3x plus 2 all squared is equal to 64. Expanding, we get x squared plus 3x squared plus 4 root 3x plus 4 minus 64. Put everything on one side. So this is 4x squared plus 4 root 3x minus 60. Divide through by 4, and we get x squared plus root 3x minus 15. And most likely going to need a quadratic, so x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And this is going to give me minus root 3 plus or minus 3 plus 60, so root 63 over 2. And since x is a length, I'm going to choose the positive number for obvious reasons. And that looks like it's 3 root 7. And there you go. So minus root 3 plus 3 root 7 over 2 is my value for x. Minus root 3 plus 3 root 7 all over 2 looks like choice C. The solutions of the equation z to the power of 4 plus 4z cubed I minus 6z squared minus 4zi minus I equals 0 are the vertices of a convex polygon in the complex plane. What is the area of the polygon? The first step in this question is to analyze that equation right there. And a little bit of a trick involved, not extremely fancy trick, is we want to get this in a certain form. We want to get this in a form that can be factored, and currently it can't. So what I'm going to do is add to both sides 1 plus I to that side, and then add it to this side, 1 plus I. And the remaining equation will stay exactly the same. And if I do that, the good news is that this side just becomes 1 plus I. And this side over here, this I cancels with that I, and I'm just left with the following. Z to the power of 4 plus 4z cubed I minus 6z squared minus 4zi plus 1. And this, the good news is factors beautifully. Z plus I all to the power of 4. And that equals 1 plus I. And this will allow us to find out what exactly the roots are. So to figure out the roots, it's a little unconventional, right? We have to do a little bit of substitution. Let w equal z plus I. Makes it a little bit easier for me. So this becomes w to the power of 4. And then this 1 plus I that I have, I'll let that be a to the power of 4, like this. All right? Now, once you want to find the roots of w, if you look at this one, that equation, w will be a, keeping in mind that these are complex numbers. It could be also IA, it could be minus a, or minus IA. Those are the 4 roots. And that's it. Those are the 4 roots, and now we have to plot them and see what we get. So if you plot this, it will look something like the following. This is x and this is I, because remember we're talking about the complex plane. If you plot these 4 points, a goes here, minus a obviously here, IA is up here, and minus IA is down here. And this is my shape. And as you can clearly see, that this shape is a square. So I have to figure out the area of this square. How do I figure out the area of that square? Well, there's several ways, obviously. You know that if you have the length of a side, obviously it's just the side squared. But I'm going to do it in a slightly different way. I'm going to do it by figuring out this length. I think that's the easiest. And if I do, I'll call that, let's say, D. D for diagonal, or actually it's half the diagonal, but I'll just call it D. And if I do, watch, the area becomes, this is also going to be the same, right? In terms of the length, that's also going to be D. This is a square. So using triangles, that's a triangle obviously, it's going to be 4 times those 4 triangles, and each of those is 1/2 base times height. The base is D, the height is D, and that is equal to 2D squared. So if I can figure out the value of D, then I can solve this area. Well, what is D? D is from here to here, right? And that basically represents the magnitude of A. That is not absolute value, it's magnitude, that symbol, because we're talking about complex numbers. Now what is A? A is 1 plus I. So using that equation, if A to the power of 4 is 1 plus I, that means if I take the magnitude of A, it'll be to the power of 4. That will be equivalent to the magnitude of this number. And how do you figure out the magnitude of a complex number? You take this number and square it, and then you take the coefficient in front of the I, which in this case is 1, and square it. You add those, and then you take the square root. So in this case, it's root 2. And that is A to the power of 4, like that. So if you just want the magnitude of A, you'd have to take root 2, which is just 2 to the power of 1/2, and take the quarter exponent of it, and therefore magnitude of A is equal to 2 to the power of 1/8, like that. So we now can figure out the area, because magnitude of A is just representing D. So we have 2 to the power of 1/8 representing D. So this is 2 times D squared, which is 2 to the power of 1/8, all squared, like that. So this becomes 2 times 2 to the power of 2 over 8, which is a quarter. And then adding exponents, we get 2 to the 5 over 4. And that's the area of this square, which is what they wanted, 2 to the power of 5 over 4. So number 23, the answer is D. Triangle ABC has angles C equal to 60 and BC equal to 4. Point D is the midpoint of BC. What is the largest possible value of the tangent of angle BAD? Here is our diagram for our triangle ABC, and let's start labeling as much as we can. We are told that BC is equal to 4, so this whole length is 4. And we are told that angle C is 60 degrees, so there is 60 degrees. And then we are interested in the tan of BAD. BAD is that angle right there, and we can call it theta. So we want to maximize the tan of theta. And we will draw perpendiculars down from B to AC to meet at F, and another perpendicular from D down to AC to meet at D, and those are going to be right angles since they are perpendiculars. And since those are 90 degrees, this is 90 degrees, and therefore this angle in here will be 30. And very similarly, since this is 90 and this is 60, this angle right here will be also 30 degrees. And we therefore have two 30, 60, 90 triangles, and since the ratio of the sides are 1, 2, and root 3, these sides will be 1, and that's already been labeled as 2 since it was half of 4. And the reason we know it's half is because D is the midpoint of BC. And in a very similar way, we can calculate this distance, since this is also a 30, 60, 90 triangle, and this is 4, and therefore this has to be 2, considering the fact that the ratio of the sides are always 2, 1, and 3 for any 30, 60, 90 triangle. And therefore, since this is 2 and this is 1, that means this distance is 1. So that's how we labeled those. So that completes the labeling of our diagram. And for completeness, we can also call BF a certain distance, and that's pretty easy to figure out. That will be just 2 root 3, again using the 30, 60, 90 diagram relationship. And the actual length of DE is root 3. So I'll just put that root 3 right there. Now at this point, we need to start labeling CA, and I'll let CA equal x. So this whole distance from here to here will be x. And therefore, the distance from A to F will be x minus 2. So that is the labeling of our diagram. We are interested in tan theta. Now tan theta, if you look at the diagram, is the division of a big angle, which is BAF, into two parts. The first part, of course, is this one, DAF, and the other part is the one we're interested in, which is BAD. So if you write it out, it's angle BAF subtract angle DAE, like that. And if you recall, there is a tan rule. The tan rule states that the tan of A minus B is equal to the tan of A minus the tan of B, all divided by 1 plus the tan of A, the tan of B, like that. And before I substitute everything into here, let's just do this on the side. Makes it a little bit easier for us. Tan of BAF, let's just calculate that. Looking at this diagram, the tan of BAF will be 2 root 3 over x minus 2, right? That over this. Opposite over adjacent. And the tan of DAE will be DE over EA. So that's going to be just root 3 over x minus 1, because remember we have to add that. All right, so now we can proceed with this equation using our tan rule, which is right here. So it's going to be tan of BAF, which is 2 root 3 over x minus 2, minus the tan of DAE, which is root 3 x minus 1, all over 1 plus 2 root 3 x minus 2 times root 3 x minus 1, like that. And simplifying, after you do all the algebra, you get root 3x all over x squared minus 3x plus 8. And this is what we have to maximize. Now, before we approach this problem at this point, there's something that I need to refresh your memory on, and it's AMGM. AMGM stands for arithmetic mean, geometric mean. And arithmetic mean, geometric mean states the following. If you have any two numbers and you take the arithmetic mean, which is just the two numbers added divided by 2, they will always be greater than or equal to the geometric mean, which is the two numbers multiplied under the square root sign. Okay? That is the AMGM rule. So I will apply that to this in a slightly tricky way. So this equation, first and foremost, I will manipulate it as follows. I'm going to just get rid of the square root of 3 and just concentrate on this part right here. Okay? But I'm going to flip it like this. And if I flip it, I'll be able to factor it like this. X plus 8 over x minus 3. And then at the end, we'll come back and put everything together. Now, you'll notice this plus this can behave as my a plus b, as follows. X plus 8 over x all over 2, using AMGM, is going to be greater than or equal to x times 8 over x, all under the square root sign, exactly like AMGM. Okay, so this is perfectly allowable. Now, simplify this a little bit. X plus 8 over x, bring the 2 over, and notice in the radical, the x's cancel, so I just get root of 8. Now, bring in the 3's. Subtract 3 from what side? Because I want it to look exactly like that, and I have made it look exactly like that. So now I've got x plus 8 over x minus 3 is greater than or equal to. Root 8 is 2 root 2, so 2 times 2 root 2 will be 4 root 2 minus 3. Okay, so far so good. Now at this point, this is exactly this, correct? But this represented this equation. But I want my original equation, so what do? I have to flip this. So first, let me write this in this form, which is exactly what it was. X squared minus 3x plus 8 all over x, and that's greater than or equal to 4 root 2 minus 3. But I have to flip it to make it look like that original form, so no problem. X over x squared minus 3x plus 8. And then this sign has to flip, less than or equal to 1 over 4 root 2 minus 3. Okay, so far so good. Now, to make it look identical to tan theta, I have to add a root 3. So let's do that. Root 3 x squared minus 3x plus 8 is less than or equal to root 3 over 4 root 2 minus 3. And this is tan theta. So tan theta is less than or equal to root 3 over 4 root 2 minus 3. So that means tan theta, the maximum it could be, is if it is equal to this. And that is root 3 over 4 root 2 minus 3. And therefore, this is the maximum value, root 3 over 4 root 2 minus 3. Root 3 over 4 root 2 minus 3 is choice D. A sequence A1, B1, A2, B2, A3, B3, ... of points in the coordinate plane satisfies AN1, BN1 is equal to root 3 AN minus BN, root 3 BN plus AN. for n equals 1, 2, 3, dot, dot, dot. Suppose that A100, B100 is 2, 4. What is A1 plus B1? We have to start somewhere in this question, so obviously we will start with just A1, B1 and work our way forward. And just for simplicity, I will let A1, B1 just be X and Y like that. So entirely using this formula, let's proceed with A2 and B2. And I'll leave the algebra up to you. I'll just give you the summary. If you do the algebra involving this, you get the following result: root 3x minus y, root 3y plus x. Continuing, A3, B3, you will get 2x minus 2 root 3y and 2y plus 2 root 3x. Continuing for A4, B4, you will get the following result: minus 8y and 8x. And this is a pattern that continues, and you can conclude at this point that an plus 3 and bn plus 3 will be negative 2 to the power of 3 bn, 2 to the power of 3 an. Just like how we got this right here. This pattern will repeat itself if you continue to do the algebra. So let's continue in this same pattern. And you get A7, B7. Let's just concentrate on every third one since we have a formula for every third one. A7, B7 will give you minus 2 to the power of 6x minus 2 to the power of 6y. A to the 10, B to the 10 will give you 2 to the power of 9y and minus 2 to the power of 9x. A to the 13, B to the 13 will give you 2 to the power of 12x and 2 to the power of 12y. And if you keep going in that pattern, you will be able to conclude that A100, B100 is equal to minus 299y and 2 to the 99x. Okay, so at this point, we know from the question that A100, B100 is 2 and 4. They've given that in the question. So now we can solve for y and x. So solving for y, we get that 2 is equal to minus 2 to the power of 99y, and therefore y is equal to 2 over minus 2 to the power of 99. And solving for x, you get x is equal to 4 over 2 to the power of 99, like that. And recall our x and y were representing a1 and b1. So if we want to figure out a1 plus b1, then that is just going to be x plus y. X is 4 over 2 to the power of 99, and then we are going to be adding negative 2 over 2 to the power of 99. So that becomes 2 over 2 to the power of 99, and simplifying, it's 1 over 2 to the power of 98. 1 over 2 to the power of 98 is answer choice D for number 25.